Okay, so here we are in question 1. We've got two particles P and Q of masses m and 0.3 kilograms respectively are at rest on a smooth horizontal plane. P is projected at a speed of 5 meters per second directly towards Q. And after P and Q collide, P moves with a speed of 2 meters per second in the same direction as it was originally moving. I want to find in terms of m the speed q of the collision. Now, as you've seen, I've drawn a diagram here. I think that's really helpful, by the way. Always draw a diagram. So we've got the situation before the collision here and the situation after the collision. And I've labeled the velocity of q after the collision v. That's the thing that we don't know. Well, what's the key principle here? Basically, this is conservation of momentum, which is that the momentum before must be the same as the momentum after the collision. So what we're going to do is we're going to calculate the momentum before. I'm going to call that P1, and that's going to be equal to the mass of P times by the velocity of P, so that's 5m, plus the momentum of Q, which is the mass of Q, times by the velocity of Q, which here is 0. Okay? So we get 5m plus 0, which is just 5m. All right. Now, what about after the collision? We'll call that P2. Well, we're going to have the mass of P, which is m, times by the velocity of P. So we get 2m. And then we're going to have the mass of Q, which is 0.3, times by the velocity of Q, which is v. So I'm going to write that as 3/10 times by v, because 0.3 is the same as 3/10. Now then, conservation of momentum states that the momentum before must be equal to the momentum after. So that's really the key bit of knowledge there. And so we can say that 5m is equal to 2m plus 3/10 v. And so 3m is equal to 3/10 v. And we want to find v, therefore, so I can divide both sides by 3 and times both sides by 10. So v is equal to 10m meters per second. Okay, so now that we've done that, we can go to part B. So after the collision, Q moves directly towards a third particle R, which I've drawn here, of mass 0.6 kilograms, which is at rest on the plane. So at rest means it's 0 meters per second. Q is brought to rest in the collision, so Q becomes 0 meters per second. And R begins to move away with a speed of 1.5. We want to find the value of m. Well, we're just doing the same thing, basically. So we now know that Q is moving with a velocity of 10m meters per second. So let's label that on. 10m meters per second. So the momentum before is equal to 0.3 times by 10m. So 3 upon 10 times by 10m plus momentum after, which is 0.6 times by 0, so that's just 0. So here what we got is we got 3m. And the momentum after, well, the momentum of Q is 0.3 times by 0, so that's 0. Plus the momentum of R, which is 0.6 or 6/10, times by 1.5, which is 3 upon 2. Okay, so I can just cancel off a little bit, can't I? So I can divide top and bottom by 2, so that's 3/5. Okay, so I'm going to get 9 upon 10 there. 9 upon 10. All right. Well, again, we just say that P1 must be equal to P2. Momentum before is equal to momentum after. So 3m must be equal to 9/10. So m must be equal to 3/10. And 3/10 is 0.3 kilograms. Okay. So that's our mass of the particle. Okay, so we're in question 2. Here we've got a particle of mass 0.4 kilograms is projected vertically upwards from horizontal ground with speed 10 meters per second. Want to find the greatest height above the ground. Okay, well, I've given a diagram, even though it seems a bit redundant. So displacement I'm taking from the ground, so that's s is equal to 0. The positive direction is going up, which means that our initial velocity, which is 10, is positive because it's going up. Whereas acceleration is negative, right? Because acceleration due to gravity is always going down. Where is the maximum height? Well, the maximum height is the point where velocity is equal to 0. If you think about that for a second, the velocity goes up, it's positive, and then as it comes down, it's going to be negative. So if it goes from positive to negative, it must have crossed through 0. So what can I do? Well, I can use v squared equals u squared plus 2as. Our v is 0, so we've got 0 squared. Our u is 10, so 10 squared plus 2 times by negative 10 times by s. We rearrange that, we're going to get 20s is equal to 100, so s is equal to 5 meters. And of course, alternatively, what we could do is we can consider energy. We could say that the kinetic energy lost, beg your pardon, must be equal to the gravitational potential energy that was gained. And the formula for kinetic energy is a half mv squared. And the formula for gravitational potential energy is mgh. Well, in this case, the m's are going to cancel off, so we don't have to worry about those at all. And our initial velocity was 10, so we've got a half times by 10 squared is equal to g, which is 10, times by h, which in this case we call s. So 10 squared is 100, divided by 2, 50, divided by 10, 5. So again, we get 5 meters. So it doesn't matter which method we use there, it gets the same answer. Okay then, well, part B, when P reaches the ground again, it bounces vertically upwards. At the first instant that it hits the ground, P loses 7.2 joules of energy. So kind of what we've got to consider is what was the energy before it hit the ground and what's the energy that it has after it hit the ground? Well, before it hit the ground, so the energy before, what we could do is we could just actually consider the kinetic energy it had when we launched the object. Right? Because basically, when we launched the object, it had a certain amount of kinetic energy. And even though that energy gets transferred to gravitational potential energy, the same total amount of energy always remains the same, even to the point where it hits the ground. Okay? So what we can do is we can calculate that kinetic energy. So let's do that. The kinetic energy before was a half mv squared. So we've got a half times by 0.4, I think it was. Just double check that. The mass was 0.4. Yeah, 0.4 times by v squared, which was 10 squared. Okay. All right. So if we multiply that all out, we've got 100 times by 0.4, which is 40. Halved is 20 joules. Okay, then. So the energy after it hits the 4 is going to be that 20, but minus 7.2. We're going to do 20 minus 7.2. And if we do that, we're going to get 12.8 joules. So that's the energy after the collision, which means this is the energy it has as it's going up. Well, if we know that, then we can calculate the kinetic energy it has here, because that kinetic energy should now be equal to 12.8. So we can take the formula for kinetic energy, a half mv squared is equal to 12.8. We can find out our new velocity. So let's do that. Got a half times by 0.4 times by v squared equal to 12.8. So we've got 0.2 times by v squared is equal to 12.8. So we do 12.8 divided by 0.2, which gives us 64. So v squared is equal to 64, which means that v is equal to 8. Right? So that's going to be well, plus or minus 8, but I mean 8 going up is what we know. So it's 8 meters per second going up. All right, then. If then this is our new initial velocity, so let's label that. U is equal to 8 meters per second going up. We find the time that it takes until it hits the ground. Well, yes. So the particle is going to do that. Up. And it's going to hit the ground here. Well, what's the condition here on the floor? Well, the condition is that this is where displacement is 0, isn't it? Right? That's the displacement equals 0 line. So we're really asking the time it takes until s is equal to 0 again. So we're going to use our formula. S is equal to ut plus a half at squared. Our s that we're interested in is 0. Our u is the 8 that we've just calculated, plus a half times by minus 10, because acceleration due to gravity is going down, t squared. Well, we can factorize this. And you get t bracket 8 minus 5t. The t is equal to 0 we're not interested in because that's the condition as it's leaving the ground. So the other one that we're interested in is 8 divided by 5, which is 1.6 seconds. Okay, so that's how we can find the time that it took before it hit the ground again. Okay. Okay, question 3. A particle moves in a straight line starting from rest. That means velocity is 0 when t is equal to 0. The displacement of the particle from a fixed point on the line at time t seconds is given by this thing here. We want to find the value of s when the particle is again at rest. In other words, we want to find the displacement when the velocity of the particle is 0. Okay, well, to do this, basically, we need to know a definition. The velocity is equal to the rate of change of displacement with respect to time, right? That should be fairly simple to understand if we just think about it for a second. Velocity is how much is your displacement changing every second, okay? So this is ds dt, okay? So what we've got to do if we want to find velocity is we just got to differentiate our displacement. So if I differentiate, I'm going to get 5 upon 2 t to the power of 3 upon 2 minus 15 upon 4 times by, bring the 3 upon 2 down, t to the power of a half, and then 6, if I differentiate it, I just get 0, right? Because it's a constant term. Okay, then, I want to find when the velocity is 0. So find t when v is equal to 0. So I'm going to set this thing equal to 0 here. So I've got 5 upon 2 t to the power of 3 upon 2 minus, well, I've got 15 times by 3, that's 45, over 8 t to the power of a half. Well, I think probably what I can do is I can factorize a little bit. I can pull out t to the power of a half, and that's going to give me 5 upon 2t. If you're not sure about that, right, I do power of 3 upon 2 minus a half. 3 upon 2 minus a half is power of 1. Minus 45 upon 8t. Oh, sorry, not t. T to the power of 0, which is just 1, right? Because I've already factorized out the t to the power of a half. Well, okay, well, that's either got solution t is equal to 0, which we're not interested in, or we've got 5 upon 2t minus 48 upon 45, beg your pardon. Sorry about that, my handwriting. 45 upon 8. I better just change that as well. 45 is equal to 0. Okay, so if I rearrange that, then t is going to be equal to 45 upon 8 times by 2 divided by 5. And if I do that, then I can cancel off some things. So divide top and bottom by 2, that becomes 4 there. Divide top and bottom by 5, and that's going to become 9. So we've got t is equal to 9 upon 4 seconds. Okay. All right, then. Well, I want to find the displacement at that particular value. So why don't I just go over here? So when t is equal to 9 upon 4, then s is going to equal to 9 upon 4 to the power of 5 upon 2 minus 15 upon 4 to the power of times by 9 upon 2, sorry, 9 upon 4 to the power of 3 upon 2 plus 6. And what does the power of 5 upon 2 mean? Well, the 2 on the denominator here means square root. So I'm square rooting this, and then I'm doing it to the power of 5. So let's square root it first. I get 3 upon 2 to the power of 5. I've got minus 15 upon 4. Again, if I look at power of 3 upon 2 here, then the denominator 2 means I'm square rooting. So this is 3 upon 2 to the power of 3, and then plus 6. So let's try to simplify all of that. So I'm going to get 3 to the power of 5. So 3 to the power of 5, I'll just do on my calculator, is 243 over 2 to the power of 5. Whoop, 2 to the power of 5 is 32 minus 15 upon 4. 3 to the power of 3 is 27, and 2 to the power of 3 is 8 plus 6. So again, if I simplify this, this is 243 upon 32 minus, let's do 15 times by 27, is 405 upon 32 plus 6. Well, let's write 6 as 32ths as well, since that looks like what we'll have to do. So that's 192 upon 32. So we're going to do 243 minus 405 plus 192 equals 30. That's 30 upon 32. If I divide that by 32, 15 upon 16, or 0.9375. So we write 15 upon 16, or alternatively 0.9375 meters. Okay. Okay, so here we are in question 4. I haven't reproduced the text of the question because there's quite a lot of text. It fills up the screen, and most of the information is represented on the graph anyway. So first part, part A, we want to find the distance traveled by the particle in the first 10 seconds of its motion. Well, this is a velocity time graph, and hopefully you know that for a velocity time graph, the displacement is equal to the area under the graph. So if you're not sure about that, I'm just going to state that main idea. Displacement is equal to the area under a velocity time graph. And just by the way, if you're not entirely sure about that, actually that should sort of make some sense, because we know that velocity is equal to the rate of change of displacement. It's ds dt. And so therefore, actually, if we invert that, then s is going to be equal to the integral of velocity with respect to time. And what does integration tell us? Well, it tells us the area underneath the curve. So if we are integrating the velocity, which means we're finding the area under the velocity curve, then what we're getting is we're getting displacement. So hopefully that should make sense to you. All right, then, we want to find this area, don't we? So basically, we just got to find the area of this triangle here. Okay, what's that area of the triangle? Area of the triangle is going to be equal to a half the base, which is 3, times by the height, which is 9/10. Okay. What's the area of this rectangle here? That area is going to be just base times by height. So that's going to be 6 times by 9/10. And what's this triangle here going to be? Well, it's going to be a half base, which is 1, times by the height, which is 9/10. Okay, so total is just got to add them up. So we can actually factorize out 9/10, can't we? 9/10 bracket 3 upon 2, which is 1.5, plus 6, plus a half, 0.5. So that's going to be 2, 8. 8 times by 9/10. So 8 times by 9 divided by 10. So that will be equal to 7.2. The distance traveled should be 7.2 meters. Okay, then, well, let's go down to part B. I think I'll drag this up. Given that t is equal to 12, find the minimum velocity of the particle. Okay, so the minimum velocity is going to be defined by whatever this value is here. That's v. Now, the key thing that we're told in the text of the question is that basically at this point, we return back to our starting point. So that means that our displacement here needs to be 0. Well, that means that the displacement that's happening in this part of the curve needs to be equal to negative 7.2, right? Because if you think about it from here to here, we're traveling in the positive direction. We move a displacement of positive 7.2. And in this section, what we're doing is we've got negative velocity, so we're moving back. We want to move back a total of minus 7.2. So this is just the area of a triangle again. So the area of this particular triangle, area, is equal to a half the base, which is t times by 10, t minus 10, beg your pardon, times by v, is the height of our triangle. And what we're told in the question is that t is equal to 12. So this is going to be a half. 12 minus 10, well, 12 minus 10 is 2. A half of that is equal to 1. So this area is just equal to v. And what do we want? We want that area to be equal to the 7.2. So v must be equal to 7.2 meters per second. But of course, this is negative, isn't it? So the velocity is rather, to be more precise, is equal to negative 7.2 meters per second. Okay, then for part C, given instead that the greatest speed of the particle is 3 meters per second, find the value of t and hence find the average speed of the particle for the whole motion. Well, what does that mean? Well, it means basically that this velocity here is equal to negative 3, right? Because the speed is just the magnitude of the velocity. So this is negative 3 meters per second, which means that this t is now the thing that we have to find. And again, what we want is we want the area under this section of the graph to be equal to 7.2. So what can we do? Well, I'm just going to get rid of this working here. So we can reuse this. The area must be equal to a half the base, which is t minus 10 times by v. In this case, our v is equal to 3. I'll keep it as a positive, I think. Right, so we can say this is a half t minus 10 times by 3. And we want that area to be equal to 7.2. Okay, 7.2. So all we got to do is just got to rearrange this basically. So I'm going to times 7.2 by 2. Okay, so that's 14.4. So 14.4 is equal to 3 times by t minus 10. So divide through by 3. Okay, so I get 4.8 is equal to t minus 10. And so therefore t is equal to 14.8. Okay, so that's the time of the particle. 14.8 seconds. And then what's the next part of this question? Well, we want to find the average speed of the particle for the whole of the motion. What's average speed going to be? It's going to be distance divided by time. So what's the total distance that's traveled? Well, it's traveled the distance of 7.2 between 0 and 10 seconds. And it's also traveled a distance of 7.2 between the 10 and the t seconds, right? Because it's gone back on itself. So it's gone 7.2 meters forward, then another 7.2 meters back. So it's traveled a total of 14.4 meters. So what's the average speed? We can go over here. So average speed is equal to the total distance, which is 14.4, divided by the total time, which is 14.8. And if I just put that into a calculator, what I get is 0.972. So 0.972, or I think 0.97 is sufficient, isn't it? Is it 2 significant figures or 3 significant figures? 0.973, 3 significant figures. All right. Okay. All right. And that's the answer to that question. All right, next question. We have 4 coplanar forces acting at a point. The magnitudes are F, 10, 50, and 40 newtons. Directions of the forces are shown in the diagram. Given that the forces are in equilibrium, find the value of F and the value of theta. Okay, well, what we want to do is we want to resolve the forces in the horizontal and vertical directions. So we're going to start in the horizontal. So we can take that force F, we can split it into horizontal and vertical components like that and that. And with a little bit of trigonometry, we should be able to see that the vertical is going to be F sine theta, and the horizontal is F cos theta. Now, if you're not sure about that, let's just review that very, very quickly. Let's label the vertical as Y. Let's label the horizontal as X. Then trigonometry will tell us that cosine of theta must be equal to the adjacent, which is X, divided by the hypotenuse F. So we're going to get X upon F. And sine theta will be equal to the opposite, which is y upon hypotenuse. So we get y upon f. And of course, if we rearrange that, then we get x is equal to f cos theta, and y is equal to f sine theta, right? So basically, we're going to be doing that for all of our forces. Okay, so I'm just going to get rid of that. So let's go round one by one. So for the F force, the horizontal is F cos theta. For the 10 Newton force, it's just purely 10 because that force is acting purely horizontally. For the 50 Newton force, the horizontal component is 0 because it's acting perfectly vertically. For the 40 Newton force, the component is 40 cos 60, but it's acting to the left. So this is a negative 40 cos theta because it's acting in the opposite direction. And because these are in equilibrium, all these are going to sum to give 0. So let's simplify this. We're going to get F cos theta plus 10. Now, sorry, not cos theta there. I meant to write cos 60. Do beg your pardon. That should be cos 60. Cos 60 is equal to half. So we've got minus 40 times by half, which is minus 20. And so this simplifies to give F cos theta is going to be equal to 10. Okay, well, now what we can do is we can do the same thing in the vertical direction. So if we do the vertical direction, we're going to get F sine theta. The 10 Newton force has got no vertical components, that's plus 0. The 50 Newton force is acting vertically down, so that's minus 50. The 40 newton force is 40 sine 60 degrees. And that must all sum up to equal 0. So let's try to simplify that. That's going to give us f sine theta minus 50. Sine 60 is root 3 upon 2, so that's plus 20 root 3 is equal to 0. And that means that we can write that f sine theta is equal to 50 minus 20 root 3. Well, okay, how can we find the angle and the value of the force? Well, the best thing to do is to take this thing and divide it by that thing. Why is that? Well, because if I write f sine theta divided by f cos theta, then what's going to happen is the two f's are going to cancel out. We're going to be left with sine theta divided by cos theta, and that's going to be tan theta. So our f sine theta is 50 minus 20 root 3. Our f cos theta is 10. So what we can see here is tan theta is going to be equal to 5 minus 2 root 3. So tan theta is going to be equal to 5 minus 2 root 3. Well, in that case, all we need is to use our calculator. So let me just get that. So tan inverse 5 minus 2 root 3. And what I get is 56.9 degrees. Theta is equal to 56.9 degrees. Well, okay. Well, then how can I find my value of f? Well, I can just substitute it in, can't I? To, for example, this one, f cos theta is equal to 10. So I'm going to take the cosine of that 59 degrees, or 56.9 degrees rather. And I can say that since f cos theta is equal to 10, the f is going to equal to 10 divided by that cosine theta. I'm going to do 10 divided by that. I get 18.32. Okay, so I get 18.3 newtons there, and that's going to be my f. Okay, well, let's carry on with part B. Given instead that f is equal to 10 root 2 and theta is equal to 45, find the direction and exact magnitude of the resultant force. Well, we've just got to do the same thing, really. So I'm going to drag my diagram down, drag that down, drag that down. Okay, so let's do all the horizontal forces, which I'll call x. Okay, so that's going to give me f, which is 10 root 2 sine 45. Now, sine 45 is 1 upon root 2. The 10 newtons is just 10, right? Because it's purely horizontal. The 50 newtons is 0 because that's vertical. And then minus the 40 cos 60. And as we said, cos 60 is a half. So we can replace that cos 60 with a half. Okay, well, if we simplify that, then the root 2's are going to cancel off. So we're going to get 10 plus 10 minus 20, and that's going to equal to 0. Okay, so there's actually no horizontal component. Well, what about the vertical components? Well, we're going to do f, which is 10 root 2, times by the sine 45 degrees, which is 1 upon root 2, plus the vertical component of the 10, which is 0, because there's no vertical component, minus the 50 newtons, and plus the 40 sine 60 degrees. So let's simplify that. Again, the root 2's are going to cancel. Gone, gone. We've got 10 minus 50, which is negative 40. And sine 60, again, is root 3 upon 2. So that's plus 20 root 3. Well, here's where we need to actually plug numbers into calculators, right? So we've got minus 40 plus 20 root 3. And what we get with that is negative 5.36. Now, remember what we were told is we were told in the question to find the exact magnitude of the resultant force. Well, what this tells us is that the resultant force acts down, and it's negative. So what I need to do, if I want to find the magnitude of this, is I just basically need to turn it into a positive, right? So how do I turn it into a positive? Say the magnitude is 40 minus 20 root 3 newtons acting down. The last bit there, you just need to be a tiny bit careful. You want to check whether or not the force is acting up or down. It's acting down. So I times it by -1 to give it a positive magnitude, and I specify that it's acting vertically down. Okay. Okay, so here we are in the next question. We've got two particles P and Q of masses 0.2 and 0.1. Attach the ends of a light inextensible string. String pass over a fixed smooth pulley, which is attached to two inclined planes. Particle P lies on a smooth plane, AB, which is inclined at 60 degrees. Particle Q on a plane BC, which is inclined at an angle of theta. String is taught and the particles can move on the lines of greatest slope. It is given that theta is equal to 60 degrees. Sorry, I beg your pardon that. The plane BC is rough and the coefficient of friction is 0.7. So let's write that on. So mu here is equal to 0.7. And we want to determine whether or not the particles move. Okay, well, the first thing to do really is always draw a force diagram, I think. So for P, we're going to have the weight acting vertically down. And that's going to be equal to 2 newtons, because 0.2 times by 10. There will be a normal reaction force perpendicular to the plane, like that. And there'll be a tension acting on the string like that. I think it's probably helpful as well to separate our weight forces into components parallel and perpendicular to the plane. So here's perpendicular, here's parallel. Sorry about that, not very good. And this angle here, right, that angle is 60 degrees just by using a bit of trigonometry. And so this length here is going to be 2 sine 60 degrees. Okay, now 60 degrees is root 3 upon 2, so 2 times by that is just going to be root 3. So that's root 3 there. And this one here is going to be 2 cos 60 degrees. Cos 60 degrees is a half, so 2 times by half is 1. So there we go. So we got our components there. Well, let's have a quick look at Q as well. Q, again, what we've got is the weight that's acting vertically down, and that's going to be 0.1 times by 10, so that's 1. There's a normal reaction force perpendicular to the plane. I'm going to call that R. And there's a tension acting like that up the plane. And of course, there is going to be a friction, but at the moment, I'm not going to draw the friction on. I'm going to leave that as it is. And I'm going to include the components parallel and perpendicular to the plane as I did already. Again, this angle here is going to be theta, which in this case is 60 degrees. So the parallel component is going to be 1 sine theta, which will be root 3 upon 2. And the perpendicular component will be 1 cos theta, which is going to be a half. Okay, so that is our force diagram. Now, we're going to want to calculate the value of limiting friction. And in order to calculate the value of limiting friction, we need to know the normal reaction force at Q. So what we're going to do is we are going to resolve perpendicular to the plane. Okay, now then, if we resolve perpendicular to the plane in this direction, we know that the forces must sum to equal 0. And the reason for that is the particle is moving parallel to the plane, right? It's not moving perpendicular in any way at all. And if it's not moving perpendicular to the plane, it means that the sum of the forces perpendicular must be equal to 0, because it's got to be in equilibrium. So we can say that R must be equal to the half, right? The component of the weight that's acting perpendicular to the plane. Well, if that's the case, we can then say that limiting friction, F limit, is equal to mu times by R. And mu in this case is 0.7. So we've got 0.7 times by half, which is 0.35 newtons. So basically what we've got to really determine is whether or not the forces that are acting on Q are going to be sufficient to overcome this limiting friction and hence for the particle to move. So how can we do that? Well, we considered both P and Q separately just a moment ago, but now what we can do is we can kind of consider it as one whole system, right? Because the tension is carried through the string. So the component that's pulling on P parallel to the plane here, root 3, is going to be countered by the component of the weight on Q acting parallel to the plane, which is root 3 upon 2. So we just got to ask, well, which one of these is bigger? Is it root 3 or is it root 3 upon 2? Well, it's root 3, isn't it, right? So basically, we know that if the particles are going to move, then the direction they're going to move is going to be P down the plane and Q up the plane, right? Because this component of the weight is bigger than this component of the weight, okay? Well then, what is that resultant force going to be on Q? Well, it will be the root 3 coming from P pulling up. So that's basically going to be like carried through the tension, minus the root 3 upon 2 acting down. So let's try to calculate what that is. We're going to do root 3 minus root 3 upon 2. Let's see what that value is. It's going to be equal to root 3 upon 2, of course. If I key that into my calculator, root 3 divided by 2, what I get is 0.866 newtons. So 0.866 newtons. Now the question is that combined force pulling upwards on Q, is that going to be sufficient to overcome the limiting friction? Well, the answer to that is yes, isn't it? Because this force is bigger than the 0.35. So we know that the resultant force kind of pulling upwards on Q is the 0.866. We're going to have a friction then that's acting down to oppose that motion going up. The maximum value that that friction can be is 0.35. And so what's going to happen is the limiting friction is going to be reached and particle Q is going to be pulled up the plane. So you want to write a statement something like, since 0.8, it's a funny 8, isn't it? 0.866 is greater than 0.35, the particles will move. Okay. And of course, if you wanted to do a little bit overkill, one of the things you could then do is you could then actually resolve your Newton's second law equations and show the acceleration of the particles, and then you definitely showed that they move. But I think that that argument should be sufficient. All right, then let's go to part B. So it's given instead that the plane BC is smooth, so we don't have to worry about friction anymore. The particles are released from rest, and the subsequent motion, the tension in the string is root 3 minus 1 newtons, okay? I want to find the magnitude of the acceleration of P as it moves on the plane and find the value of theta. Well, in this case, what we are basically told is that, what we should understand is that theta is not necessarily 60 degrees, right? It's actually got to be different to that. So we've got to pull down this diagram. Whoa, and we've got to kind of redo our forces. So I'm going to go down here again, redo my force diagram. So this is going to stay the same on P, isn't it? So that's going to be 2 newtons acting down. The components here are going to be the same, right? So that will be, the parallel will be 2 sine 60, so that'll be root 3. And the component perpendicular will be 2 cos 60, which will be 1. We've got the normal reaction force, okay, that's not interested in it really. And we've got the tension. The tension here is root 3 minus 1. So I think it's helpful to draw that on. Same thing now with Q. We've got the weight acting down, which is 1 Newton. And we've got the components acting parallel and perpendicular. Well, in this case, the angle is theta, isn't it? So this thing is going to be 1 sine theta, the component that's parallel to the plane, and this will be 1 cos theta. Okay, and here what we got, again, we've got a normal reaction force, but we're not really interested in that. And we've got a tension that's acting up the plane, and that tension is root 3 minus 1. Well, we just need to do a little bit of analysis, right? We want to ask the question, if the particles are going to move, in which direction will they move? And to do that, we should just look at P. So here what we've got, P has got a component of the weight acting down, which is equal to root 3. And it's got a tension acting up, which is root 3 minus 1. Now, which one of those forces is bigger? Is it root 3 or root 3 minus 1? Well, obviously, it's got to be root 3, right? Because the tension is 1 less than that. Well, that means that if the particle's going to move, we know that P is going to move down, and we now know that Q is going to act up. Right? So what we can do is we can resolve forces on P in the parallel direction. So we're going to do the parallel direction for P, okay? And what that's going to give us is root 3, the component of the weight acting down, minus root 3 minus 1 acting up the plane is equal to ma, right, which is 0.2 times by a, right? So what we've done is Newton's second law, right? The resultant force, which is root 3 minus this thing, root 3 minus 1, is equal to the mass times by the acceleration. What we've got to do is just got to simplify that. So root 3 minus root 3 is 0. 1 minus minus 1 is 1. So 1 is equal to 0.2a. So therefore a is equal to 5 meters per second squared. Okay, so that's that done. All right then, well, we've got to think about what's happening at Q. So if we resolve parallel to the plane on Q, then what we're going to get is, well, we've got a tension acting up the plane, which is root 3 minus 1. Beg your pardon. And we got a component of weight acting down the plane, which is 1 sine theta. And that will be equal to the mass times acceleration, 0.1 times a. So again, we've done another Newton's second law. We've found the resultant force, which is tension acting up minus the weight component acting down, is equal to mass times acceleration. So now we just need to simplify this. And of course, we know from the previous part that a is equal to 5. So what we can say is, all right, root 3 minus 1 minus sine theta is equal to 0.1 times by 5, which is 0.5. And therefore, rearranging, sine theta must be equal to root 3 minus 1 minus 0.5, which is minus 1.5. So theta is going to be the sine inverse of root 3 minus 1.5. Well, I've just got to key that into my calculator. Root 3 minus 1.5 equals, and then sine inverse of that is 13.4. So the angle there is going to be 13.4 degrees. Okay, now guys, I think that best thing to do is to redraw your force diagrams. Because I think that one of the traps that's going to happen is you're going to take your thinking from part A and you're going to try to reuse all of your diagrams and all your working. And there are dangers with that. One of those dangers is you're going to forget that you've got to change your components here on the weight. And another danger, I think, is that you may miss the directions in which the particles are moving. So I think even though it takes a bit longer, just repeat the working because ultimately you just want to make sure you get it right. Okay? I hope that was helpful. Okay then, question 7. A car of mass 1200 kilograms is traveling along a straight horizontal road. The power of the car's engine is constant and equal to 16 kilowatts. There is a constant resistance to motion of magnitude 500 newtons. I want to find the acceleration of the car at the instant when its speed is 20 meters per second. Okay, I think it's always helpful to draw a diagram. So how is the car moving? Well, there's a driving force that's pulling the car to the right, and there's a resistance force acting to the left. Now then, I think one of the things that you need to know is you need to know the formula that power is equal to force times velocity. But I prefer not to write it as F times by V, but I prefer to write it as D times by V. The reason for that is I want to specify that the force that this power is creating is the driving force, right? If you've got an engine and it's using up power, what's it doing? Well, it's producing a driving force, right? So we want to actually specify that this particular force is the one that's being produced. Okay, then if the speed is 20 meters per second, then we can just stick the numbers into this formula. So we got, we can rearrange and say the driving force is going to be equal to the power divided by the velocity. The power is 16,000. Okay, and the velocity was 20. So we can chop. So that's going to give us 800 newtons. And then what we can do is we can just do Newton's second law, right? So Newton's second law, the driving force acting to the right is 800 minus the resistance force acting to the left, which is 500, is going to be equal to the mass, which is 1200 kilograms times by the acceleration. So 300 is equal to 1200 A. And of course, again, we can chop, right? So divide by 100 like that. So A is going to be equal to 3 upon 12, which is 0.25 meters per second squared. Okay, so that's the answer for part A. Let's go down to part B. Assuming that the power and the resistance forces remain unchanged, find the steady speed at which the car can travel. Well, look, if we're in steady speed, that means that there's no acceleration. And if there's no acceleration, then these forces must be balanced. So in other words, the driving force must be equal to the resistance force. So this is the situation we're interested in. We want the driving force to be equal to the resistive force. And the resistive force was 500 newtons. Double check that again, 500 newtons. Okay. Okay, so then, again, we're going to use the formula P is equal to the driving force times by the velocity. I'm going to rearrange that. So velocity is equal to power divided by the driving force. Okay, and the power is 16,000 because it remains unchanged. And this driving force is going to be 500. Again, we can chop. So we've got 160 divided by 5. So we can divide by 10 and times by 2. That's going to give us 32 meters per second. Okay, so that's the first part of this question. Okay, so we've got the last part of this question. We've got the car comes to the bottom of a straight hill of length 316 meters, which is inclined at an angle to the horizontal, which here I've labeled as theta. The power remains constant at 16 kilowatts, but the magnitude of the resistance force is no longer constant and changes, such that the work done against the resistive force in ascending the hill is this thing here. The time taken to ascend the hill is 15 seconds. Given that the car is traveling at a speed of 20 meters per second at the bottom of the hill, find its speed at the top of the hill. Well, as always, hopefully what you notice as I've gone through these questions is the first thing I've done is I've drawn a nice clear diagram so that I can understand what's going on. But the second thing really to understand this question is to know the work energy principle. So I'm going to have that down here. We're just going to go through it. The work energy principle states that the change in the mechanical energy of an object is equal to the work done by external forces acting on the object. Now, the thing is, guys, I reckon that many of you have been taught a different way to solve this kind of problem. The way you've probably been taught is try to think about what is the increase of the potential energy, what is maybe the decrease of the kinetic energy, and then try to balance an energy equation in some way. Now, the problem I have with that is that students then get mixed up with, am I adding, am I subtracting, is my kinetic energy going up, is my potential energy going up, where is my work going, on which side of the equation does it go, is it negative, is it positive, all of that kind of stuff. So I think that this thing here, the work energy principle, if you actually learn the kind of the technical precise definition, it's going to make all kinds of problems like this actually quite simple because it gives you one framework in which to do everything. However, at the start, it will seem a little bit more complicated. And one of the ways it's going to seem complicated is I've introduced this idea of mechanical energy. Well, what is mechanical energy? I'll call it ME. Mechanical energy is just the summation of the kinetic energy and the gravitational potential energy of your object, right? So if I was to say, going here, what's my mechanical energy for the car here? Well, what I've got to do is I've got to find its kinetic energy and its gravitational potential energy and add them up. And what's the mechanical energy here? Well, I find the gravitational potential energy and the kinetic energy and I add them up, okay? So that's mechanical energy. Now, the work energy principle states that the change in that mechanical energy, right, the change in it is going to be equal to the work done by the external forces. So what I've got to do is I've got to calculate the mechanical energy at the beginning, the mechanical energy at the end. I've got to find the difference between those two, and that difference will be equal to whatever work was done on the object. Okay, so let's try to do that. So firstly, let's try to calculate the mechanical energy at the beginning. So mechanical energy 1, I'll write it as, is going to be equal to the kinetic energy, which is a half m, which is 1,200, times by v squared, which is 20 squared, plus our gravitational potential energy, but at the bottom of the hill, that gravitational potential energy is going to be 0. So what I've got here is a half times by 1,200 times by 20 squared. So I'm just going to key that into my calculator. And what I get there is 240,000 joules. 240,000 joules. Okay. All right, then what I'm going to do is I'm going to do the same thing, but for at the top. Let me just move this guy down a little bit. Ooh. Yeah. Let's find the mechanical energy at the top. So again, I've got to have the summation of the kinetic energy. So that's going to be a half 1,200 times by v squared, with the v we don't know. And this time plus the gravitational potential energy, which is mg. So mass is 1,200, g is 10. And our height is going to be this thing here. Well, how can we find that height? We can use a bit of trigonometry. That height should be equal to 316 sine theta. Okay, then what we can do is we can combine all of this. So that's going to give us 600 v squared plus, well, sine theta is going to be 1 upon 60, right? Because that's what we're told in the question. So I'm going to do 1,200 times by 10 times by 316. And I'm going to divide it by 60. And what I'm going to get is 63,200. So 63,200. Okay, so that's my mechanical energy at the end. All right, then. What I now want to do is I want to calculate the change in the mechanical energy. And that means I'm going to do the final mechanical energy minus the initial. Right, so I'm going to take this thing, the mechanical energy at the end, and subtract it from that thing, the mechanical energy at the beginning. If I do that, I'm going to get 600 v squared, and then I've got the 60,200 minus the 240,000. So 240,000, which is minus 176,800. Okay, so that's my change in mechanical energy. Well, what does the work energy principle state? The work energy principle states that this change in the mechanical energy is going to be equal to the work done by the external forces. So let's try to think about those external forces. We've really got two forces, right? We've got the force of the driving force acting on the car, right? That's going to be increasing the mechanical energy. And then we've got the resistive force of 128,400, which is going to be decreasing the mechanical energy. So let's just try to think that one through. If we're going to have a change in mechanical energy, that change is going to be created by these two forces doing work, the driving force doing work and the resistive force doing work. But which way around is it going to be? Well, the driving force is going to be increasing our mechanical energy, right? Because that's the whole point of the engine of the car. It increases your energy. So that's going to be positive work. Whereas the resistive force is going to be decreasing your mechanical energy. That will be negative work. So we're going to have a positive work due to the driving force. We're going to have a negative work due to the resistive force. So what we've got to do is just got to calculate what those are. So if we've got constant power of 16 kilowatts, and the time that the ascension took was 15 seconds, then we can say that the work done by the driving force must be equal to the 16 kilowatts, so the 16,000, times by the 15 seconds, right? And the reason for that is power is energy divided by time. So energy is power times by time. So we're going to have 16,000 times by 15, which is 240,000 joules there. Okay. All right then. And we now also know that the work done by the resistive force is equal to, what was it? 128,400. So that's going to be negative, isn't it? Because that's going to be decreasing our mechanical energy. So what can we say? We can now say that our change in mechanical energy, which was 600 v squared minus 176,800, 600 v squared minus 176,800, that change in mechanical energy is going to be equal to the work done by the driving force to increase that energy, which is 240,000, minus the work done by the resistive forces, which is decreasing that energy. So that's the reason it's negative. So then what we've got to do is we've got to resolve this. So I'm going to have 240,000, yep, minus 128,400. And then I can add on to that the 176,800. I'm going to get that my 600 v squared should be 288,400. And so if I divide both sides by 600, I'm going to get 481. If I square root that, I'm going to get my velocity is 21.9 meters per second. Okay, and that should be our answer. Let me just check that I've understood the question correctly. Find the speed at the top of the hill, which is 21.9. Okay, now, I realize that the way I've done that may well be new to many of you, maybe a different method. It may seem like it's a bit harder than what you're used to, but my point is it should be quite easy to understand, right? That if you think about it, you've got the energy of your car, the mechanical energy. It's either going to go up or down, right? And what's going to cause it to go up or what's going to cause it to go down? Well, it's other forces doing work on the object, on the car. You got to just try to reason out in your mind, are those forces going to be increasing my energy or are they going to be decreasing my energy? If they're increasing your energy, they're going to be a positive work done. If it's decreasing, it's going to be negative work done. And I genuinely feel, in my experience, that students who kind of work it through in a nice systematic way like that are much more likely to get the answer right, rather than if you try to say, I'm going to figure out my increase of kinetic or my decrease of potential or whatever it is, and then try to balance the energy off that way. I find that when you do that, students tend to make mistakes because they're not quite sure what to do. I think with this method, at least you've got kind of one coherent way of understanding the system. Okay, I hope that was helpful.